Welcome back to the deep dive, everybody. Today we're diving into a fascinating paper, actually.
Yeah,
One that you flagged for us called Interpreting Emergent Planning in Model-Free Reinforcement Learning.
right.
Really, really interesting stuff. We're going to be talking about AI agents.
Yeah.
And you know how they learn through trial and error, right?
Mm-hmm.
Well, this paper, it explores whether these agents can actually, develop the ability
Mm-hmm.
to plan ahead, much like we humans do when we're solving a puzzle or trying to figure something out,
Yeah, it's strategically in advance.
Exactly. So, the paper that we're looking at today is 2504.1871v1.pdf. You can find it online if you want to follow along.
And it really dives into these model-free agents, specifically one called DRC.
GRC.
DRC. Yeah, and they use it to play this classic game, Sokoban.
Oh, Sokoban.
Have you ever heard of it?
Yeah. I've played Sokoban.
It's a real brain teaser.
It is. You got to push those boxes around.
You got it. You got it. Into these target locations, and it really requires some forethought.
It does. You can't just randomly push boxes.
Yeah.
You got to think a couple steps ahead.
Absolutely.
So, the big question here, and what we're going to try to unpack today for you, the learner, is, are these AI agents just sort of reacting to their environment?
Yeah.
Just responding to what's immediately in front of them? Or are they actually thinking?
Right.
Are they strategizing? Are they planning their moves?
So that's the core mystery, right?
It is. And we're going to look at how the researchers figure this out, how they peeked into the AI brain, so to speak.
Right.
And we'll discuss what all of this could mean, for the future of AI.
The implications are huge.
They are. All right, so let's jump right in. The paper dives into this really fundamental question.
Okay.
Can agents that learn without a model, a pre-programmed model of their environment, can they still plan? Because traditionally, the thinking was that to be able to plan, you need some sort of model.
Right. You needed some understanding of the world around you.
Yeah, like a blueprint or a map in your head.
Exactly.
But here's the thing, right? These DRC agents, they're doing really well in Sokoban.
They are. It's surprising, really.
And it's a complex game. It requires planning, like we said. And to make things even more interesting, their performance actually gets better when you give them more time to think before they make a move.
It's like they're using that time to actually strategize.
Right. It's not just random actions. There's something more going on.
There's got to be.
Okay, so how did the researchers figure this out?
Well, they use this technique called concept-based interpretability.
Concept-based interpretability.
It's a mouthful, I know.
It is a mouthful.
But the idea is to try to understand what kinds of concepts the AI is learning.
Okay, concepts. So, what kind of concepts are we talking about here?
So in this case, they focused on what they call multi-class square-level concepts.
Square level. So that's relating to the grid, to the squares on the Sokoban board.
That's right. It's all tied to specific locations in the game.
Makes sense.
So one example is the agent's intended future movement onto a square.
Okay. So, the AI is thinking, I want to move to that square.
Exactly. And they called this concept CA.
CA, got it.
And another one is the future direction a box will be pushed off a square. So, I'm going to push this box from this square over to that square.
Okay, so that's like a planned action.
Yeah, a planned action. And this concept is called CB.
CA and CB. So these are like the building blocks of a plan.
Exactly. The basic units of planning.
Okay, so they've got these concepts. How do they know the AI is actually using them?
That's the tricky part, right?
Yeah.
So they use these things called linear probes.
Linear probes.
Think of them like little detectives.
Okay, little detectives. I like that.
Snooping around inside the AI's brain.
Okay. So how do they work?
Well, they're trained to predict these concepts, these CA and CB concepts, based on the AI's internal activity.
So they're looking at the AI's neural network, and they're trying to see if they can predict what the AI is going to do based on the patterns of activity.
You got it. And if they can predict it accurately, it means the AI is actually representing that concept internally.
So if the probe says, hey, I think the AI is going to move to that square, and then the AI actually does it.
Bingo. It means the concept of moving to that square is active in the AI's mind.
Wow. That's pretty amazing.
And get this, the probes worked really well even when they were looking at tiny, tiny areas of the network.
Tiny areas.
Like just a single square on the game board.
So that means these concepts are very specific and localized in the AI's brain.
Exactly. They're organized spatially, just like the game itself.
So it's not just that the AI has these concepts floating around somewhere. They're mapped to the game world.
Yeah, it's like a mental map of the game with these concepts pinned to different locations.
That's really cool.
So they've shown that the AI represents these planning concepts. But that's not the whole story.
Right. Just because it has these concepts, it doesn't necessarily mean it's using them to actively plan.
Exactly. It could just be passively observing these things, not actually planning with them.
So how did they figure out if the AI was actually planning?
Well, they did a deep dive into the AI's internal representations of CB. Remember, that's the concept of pushing a box off a square.
Right. CB, the box pushing concept.
And they looked at how these representations changed over time as the AI was playing the game.
Like watching the AI's thoughts unfold.
Exactly. And what they found was really compelling.
What did they find?
They saw evidence of what they call iterative plan construction.
Iterative plan construction. What does that mean?
It means the AI wasn't coming up with a complete plan all at once.
Okay.
It was building it step by step, refining it as it went along.
Oh, so like trying different things out in its head, seeing what works.
Yeah, like a puzzle solver, trying different pieces until they find the right fit.
So it's not just pre-programmed to follow a specific set of rules.
No, it's actually figuring things out as it goes.
Fascinating.
And it gets even more interesting. They also found evidence of bidirectional search.
Bidirectional search.
It's a classic planning technique in AI.
Okay.
Where you search for a solution both forward from the starting point
Okay.
and backward from the goal.
So like working from both ends to meet in the middle.
Exactly. And they found signs that the DRC agent was doing something very similar.
So the AI is planning forward from where the boxes are.
Right.
And backward from where they need to be.
That's right. It's pretty cool, huh?
That's very cool. And it gets even cooler.
Even cooler.
They found evidence that the AI was doing this bidirectional search in parallel.
In parallel.
Meaning it was exploring multiple plan segments at the same time.
Like multitasking.
Yeah, like a super efficient planning machine.
Exactly. And if you look at figure 1 in the paper,
Figure 1.
it shows some really clear examples of this. You can actually see the AI's thoughts as it's exploring these different plan segments.
So we can actually see the planning process happening.
Yeah, it's like peeking into the AI's mind.
That's amazing. What else did they find?
Well, they also found evidence of evaluative planning.
Evaluative planning. What's that?
It means the AI wasn't just blindly trying every possible move.
Okay.
It was actually considering the consequences of its actions.
So I was thinking, if I do this, then this will happen, and that might not be good.
Exactly. It's like it's evaluating different plans and rejecting the ones that won't work.
So it's not just planning, it's planning intelligently.
Exactly. And there's some great examples of this in the paper, too.
Oh, yeah.
Yeah, figures 1A and 1B show how the AI considers a simple path,
Okay.
realizes it won't work,
Uh-huh.
and then comes up with a more complex but successful alternative.
So it's learning from its mistakes, in a way.
Yeah, it's adapting its plans based on what it's learning.
So we've got iterative planning, bidirectional search, evaluative planning. Anything else?
One more thing. They also found evidence of adaptive planning,
Adaptive planning.
meaning the AI could adjust its plans on the fly.
Okay, so it's not just sticking to a rigid plan. It can improvise.
Exactly. For example, if it's trying to push 2 boxes to the same target,
Uh-huh.
but only 1 box can fit,
Right.
it'll change its plan. It won't just keep trying to do something that's impossible.
So it understands the constraints of the game.
Yeah, it's learning the rules and adapting its behavior accordingly.
That's impressive.
It is. It really shows that the AI is not just reacting to the environment, but it's thinking ahead and planning its actions.
Now, you mentioned earlier that the AI's performance got better when you gave it more time to think.
Right.
How does that fit into all of this?
Well, that's another piece of evidence that supports the idea of planning.
Okay, tell me more.
So the researchers gave the AI extra thinking steps.
Thinking step.
Yeah, basically forced pauses before it could make a move.
Okay. And they found that the more thinking time the AI had, the more accurate its internal plan became.
So it's like the AI is using that extra time to refine its plan, to think things through more carefully.
Exactly. And you can see this in figure 6 of the paper.
Figure 6, all right.
It shows that the accuracy of the AI's plan, as measured by those linear probes, increases with more thinking time.
So it's not just randomly waiting around. It's actually using that time to improve its plan.
Exactly. It's thinking, it's strategizing.
This is really fascinating stuff.
It is. And it gets even crazier.
But there's more.
Oh, yeah. The researchers actually went a step further and tried to influence the AI's thoughts.
Influence its thoughts. How is that even possible?
Well, remember those concept vectors we talked about earlier?
The ones from the linear probes.
Yeah, exactly. They use those vectors to manipulate the AI's internal representations.
So they're like injecting thoughts into the AI's brain.
It's kind of like that, yeah.
Yeah.
They could make the AI represent specific plans just by adding these vectors to its neural network. Wow, that's mind-blowing.
It is. And they tested this out on some special levels they designed.
Special levels.
Yeah, they called them agent shortcut and box shortcut levels.
Okay.
And these levels had two possible solutions.
Okay.
One was a short, optimal solution,
Uh-huh.
and the other was a longer, suboptimal solution.
Like a detour.
Exactly, a detour.
Yeah.
And by manipulating the AI's internal representations...
They can make it take the detour.
Exactly. They could make the AI choose the longer, less efficient path.
That's by changing his thoughts.
Yeah, it's like they were planting the idea of the detour in the AI's mind.
And then the AI would actually act on that idea.
Yeah, it would follow the detour even though it wasn't the best solution.
That's incredible.
It is. It shows that the AI's internal representations aren't just passive reflections of the world.
Right.
They actually drive its behavior.
So the AI's thoughts are directly linked to its actions.
Exactly. And you can see all of this in figures 7 and 8 of the paper.
Figures 7 and 8, got it.
And table 1 summarizes the results really nicely.
Table 1, okay.
It's pretty compelling evidence.
It is. So we've seen that the AI can plan, but how does it actually learn to do that?
That's a great question. And the researchers looked into that as well.
Oh, yeah.
They wanted to see how the AI's planning abilities developed over time during its training process.
Okay.
And what they found was really interesting.
What did they find?
They found that the AI's ability to benefit from extra thinking time.
Remember those thinking steps we talked about?
Yeah, exactly. That ability
Okay.
is strongly correlated with the accuracy of those linear probes in decoding the CA and CB concepts.
So the better the AI was at representing those planning concepts internally,
Uh-huh.
the better was it using extra time to actually plan.
Exactly. The two things develop together.
Makes sense. You can't really plan if you don't have the concepts to plan with.
Right. You need the building blocks first.
Yeah.
And you can see this correlation in figure 9 of the paper.
Figure 9, all right.
It shows how the AI's planning ability and its concept representation accuracy improve together over time.
So it's a gradual process.
Yeah, it's not like the AI suddenly wakes up one day and knows how to plan.
It learns and develops these abilities over time.
Exactly. And this development was consistent across all layers of the AI's network.
All layers.
Yeah, it wasn't just happening in one specific part of the brain.
So it's like a whole brain phenomena.
You could say that, yeah. And figure 38 in the appendix shows this really nicely.
Figure 38, okay.
And the AI's ability to refine its plans during those thinking steps, that also emerged pretty early in the training process.
So it's not like it needs tons and tons of experience to start planning effectively.
No, it seems to pick it up relatively quickly.
That's interesting.
It is, and it suggests that this ability to plan might be a fundamental property of these kinds of AI systems.
Now, Sokoban is a very specific game.
It is.
Very structured, very rule-based. Do you think this planning ability is something that could generalize to other tasks, other environments?
That's the million-dollar question, right?
It is.
And the researchers actually looked into that as well.
Oh, good.
They tested the AI on some levels that were different from the ones it had been trained on,
Okay.
like levels where the agent wasn't even present.
So it had to plan without being able to see the whole board.
Yeah, it's called blind planning.
Blind planning. Wow.
And they also tested it on levels with more boxes and targets.
So more complex levels.
Exactly. And even on levels where the walls would change during the game.
So the environment was dynamic, unpredictable.
Yeah, it was like throwing the AI a curveball.
And how did it do?
It still showed evidence of planning.
Really?
Yeah, it was able to adapt its plans to these new and challenging situations.
That's amazing. So it's not just memorizing solutions for specific levels.
No, it's learning a more general planning ability.
That's huge.
It is. And you can see all the details of these tests in appendices 8.2.6 through 8.2.9.
Appendices 8.2.6 to 8.2.9. Okay.
It's a lot of information, but it's worth checking out.
Sounds like it. So, based on all of this, what kind of planning algorithm do you think the AI is using?
Well, the researchers believe it's something similar to parallelized bidirectional search.
We talked about bidirectional search before.
Right, searching forward from the start and backward from the goal.
Yeah.
And the parallelized part means it's doing this search in multiple directions at the same time.
So it's like a supercharged version of bidirectional search.
Exactly. And it's different from a lot of the standard planning algorithms used in AI.
So it's not just mimicking what we already know.
No, it seems to have discovered a new and potentially more efficient way to plan.
That's really exciting.
It is. It opens up a lot of possibilities for developing new and improved AI planning systems.
Okay, so for you, the learner, what are the key takeaways from all of this?
Well, I think the biggest one is that this research shows that AI agents can learn to plan in really sophisticated ways.
And they can do it without being explicitly programmed to plan.
Right. They can learn this ability through trial and error, just like we do.
And they can even learn planning algorithms that are different from the ones we've designed.
Yeah, they can come up with their own solutions, which is really cool.
It is. And the fact that we can use techniques like concept-based interpretability to actually see these planning processes happening in the AI's brain.
It's amazing, right?
It's amazing. It opens up a whole new world of possibilities for understanding and improving AI.
Absolutely. And it also raises a lot of new questions.
Like what?
Well, like, can we generalize these findings to other tasks, other AI systems?
Right. Could this kind of planning ability be used in other applications?
Exactly. And how can we use these interpretability techniques to, like, guide the AI's planning process?
So we can make it even better at solving problems.
Yeah. And what about the ethical implications of all of this?
Oh, that's a big one.
It is. We need to think carefully about how we develop and use these powerful AI systems.
Absolutely. Okay, this has been a really fascinating discussion.
It has.
And it leads us to a final provocative thought for you. The learner.
All right, lay it on us.
If a relatively simple AI agent, playing a game like Sokoban, can learn to plan in such a sophisticated way,
Right.
what kind of planning abilities might emerge in more advanced AI systems?
Ooh, good question.
The kind of systems that are being developed to solve real-world problems.
Self-driving cars, medical diagnosis, financial modeling.
Yeah, exactly. It's a really exciting and maybe a little bit scary thought.
It is. But it's important to think about these things.
It is. We need to understand how these systems work, how they think, how they plan.
So we can make sure they're used for good.
Absolutely.
Mm.
So keep exploring, keep learning, and keep thinking about the future of AI. Thanks for joining us on this deep dive.